In this video, we're going to discuss a synthetic strategy for benzene reactions that's called blocking. So guys, there's only one reversible EAS reaction, and that's sulfonation. Remember that sulfonation, you use concentrated sulfuric acid, it produces SO3, and that reacts, makes a sulfonic acid group. But remember that we could very easily remove the sulfonic acid with heat and acid, or even steam. That would be enough to take off the sulfonic acid group, okay? That's going to make it really special, give it a real synthetic advantage to us, okay? And this is why. Imagine that you're trying to get an ortho substituent. Remember that we talked about ortho-para directors they have ortho and para substitution, but really they're usually going to favor the para position, right? It's difficult to get things to add ortho. And when you're trying to get high yields, it's not okay to get a 15% yield of ortho or a 20% yield of ortho. Imagine if you're trying to get an 80 or 90% yield of ortho. How do you do that? The only way to do that is to block the para position. And that's the advantage of using sulfonation. Because sulfonation is actually, that's one of the biggest things it's used for. It's used to block the para position so that you can force ortho substitution. Because remember, ortho substitution is usually not highly favored because of steric hindrance. But if you can block that para position, then you're going to force ortho substitution. It's brilliant, okay? So this is called a blocking group because it's not actually found in the final product. In the end, you're not going to know that the sulfonic acid was ever there because you're going to take it off. It just was there to block the second EAS reaction. So let's go ahead and look at this. Let's say that you're trying to get some kind of substituent in the ortho position. And that's it. All you want is ortho products. You want ortho substitution. Okay? You better not just react the electrophile straight away with the toluene. In this case, we have toluene. Why? Because you're going to get so much para that it's going to be almost worthless. You're going to get very little ortho. And then you have to separate it, and you get very little yield. It sucks. But what you could do is you can do a sulfonation first. Okay? A sulfonation reaction, concentrated sulfuric acid and heat, that's going to make SO3, right? And what that's going to do is it's going to make a sulfonic acid here in the para position. Why is it going to be para? Guys, because we know that the para position is favored. In fact, this is going to be over 90% is going to be para. Okay? Very, very high yields. Okay? Now what we do is we can do our EAS reaction. So now you do your second reaction. This is our first reaction. This is your second reaction. You do an EAS, and what happens? Notice, what types of directors do you have? Well, CH3 is ortho-para director. So it's going to direct either to here, or to here. Are you guys following so far? You got the ortho positions and the para. Can the EAS reagent actually add para? No. Notice we also have a meta-director, guys. Notice that my sulfonic acid is a meta-director because you have a very, very strong partial positive here. Okay? In fact, this is one of our strong deactivators. So this is going to be what type of director? Meta. So what positions does it direct to? It's going to direct to here and to here. See what's going on? We're actually getting both groups directing to the same spots that are ortho. Okay? So now when I react my EAS, it's going to add, the electrophile is going to add specifically here. Okay? Or the other one, but they're both the same. After my electrophile has added, then I can use my dilute acid to desulfonate. And what I wind up getting is just a hydrogen here. So in the end, it's called a blocking group because it's not found in the final product. It was there simply to block the para position and allow me to produce ortho substitution. All right? So guys, that's the whole point behind this topic. Let's go ahead and do a practice problem to really reinforce this. So predict the product of the following multi-step synthesis. Do all 3 steps, and then I'll show you guys how it works.